Hi everybody, this is Karpaya from RMD Engineering College. In this video, just I'm going to explain how to design a optical fiber using OptiFiber tool. Before going to design, just let me introduce about the OptiFiber tool. It is a tool from OptiWave network. We can avail this product for 30 days as a trial for learning purpose. It is an excellent tool for learning optical fiber. Here, using this OptiFiber tool, we can design and analyze optical fiber for any requirements. I hope for ECE students, final year ECE students, they have optical and communication networks in which they have studied about optical fiber applications, attenuation and dispersion, everything. In this regard, in second unit and first unit, they have a detailed description about the optical fiber and optical fiber parameters. Using this OptiFiber tool, we can do experiment for all available problems. So to design optical fiber, we have to consider all these points. By defining these parameters, we can design optical fiber. So in OptiFiber tool, we have to define the refractive index profile for core and cladding. Then the size of the core and cladding has to be defined in terms of micrometer, and then operating wavelength has to be mentioned in terms of micrometer. There are so many fiber parameters we can consider for analyzing purpose, but here we are going to consider only very few parameters for simplicity. Number of modes present in the fiber, which define whether the fiber is single mode fiber or multi-mode fiber. Here the number of modes is inversely proportional to the wavelength. So by defining the operating wavelength, if the operating wavelength is longer, means then more number of modes will be present. If the operating wavelength is less, means then number of modes will be less. Similarly, if the core diameter or radius is large, means then the number of modes will be more. If the core size is less, means then number of modes will be less. So to define single mode fiber, we have to keep the core diameter as a small one, as well as the wavelength should be a smaller one. Then if you consider the dispersion, what material we are selecting for fiber design, based on that based on that it will offer the material dispersion. And then what is the structure, waveguide structure, based on that it offers the waveguide dispersion. If you add material dispersion as well as the waveguide dispersion, then we will find the total dispersion. Then the final last one is polarization mode dispersion. Okay, now let us get into the, as I told you, this is OptiFiber tool. It can be downloaded from optiwave.com. So using this OptiFiber tool, we can design the fiber profile. So I'm clicking design fiber, in which I am selecting refractive index profile. I'm giving OK. So I'm getting this window, fiber profile window, in which I'm adding region 0, that is nothing but core. I'm giving, for our understanding, I'm giving the name core. I'm applying. So and next region is cladding. I'm giving rename. This is cladding. Apply. Okay. So core, for core I am defining width is nothing but in terms of radius. Here we have to consider radius size. Core radius can be 5 micrometer, for example. Okay, so here I am defining the profile, refractive index profile. as a constant. If you want to design the gradient index profile means we can change the constant into the function, or we can define our own function also using the user function. Okay, and after that I'm going to design the cladding profile. For that cladding profile I'm giving the width as 65 point, sorry, 62.5. that is nothing but the diameter of the cladding will be 125 micrometer. Okay, so here the profile, refractive index profile of the cladding, I'm giving 1.46. For core I gave 1.48. For cladding I'm giving 1.46. Here the operating wavelength I'm giving 1.55, that is nothing but 1550 nanometer. Okay, now here I got the fiber profile in which this rectangle shape is nothing but this is core and this is cladding. Actually this is a cylindrical fiber. Okay, so keep this in mind. Here I'm going to design, I'm going to calculate the number of modes supported by this fiber. Okay, here I can select any mode solver method. Here I have option finite difference method and matrix method. If I want to see only the LP modes, linearly polarized modes, then I can select either this one or the second one. Or if I want to see the exact modes, TE modes, TM modes, hybrid modes means, then I can go for vector modes. Okay, for simplicity, for our representation, just I am taking this one, LP modes. So the I'm leaving remaining all those things as default. Maximum number of modes can be 10. Okay, so up to which enough. The wavelength is as I defined 1.55. Okay, so here I'm giving a recalculation. So if I give I click recalculate, then the number of modes supported by this fiber is available here. Okay, so this fiber will support LP01, LP02, LP11, LP21. Okay, suppose if I want to know the exact modes supported by this fiber means, then I can change the mode solver method to vector modes. That is nothing but if I give recalculate, then I will get TE mode, TM mode, HE11, EH11, HE12, HE21, HE31, all those modes. Okay, now these modes are combinedly represented by these linearly polarized modes. Okay, so using these options, the remaining options, we can see the modes in 3-dimensional also. For example, the LP01 is nothing but here I'm getting. Okay, so I can change the color, everything. So this is LP02. Suppose if I want to decompose these modes means, then I can see the LP02 and I can calculate. If I calculate, then I will get what is the amplitude of that LP02 mode and phase angle, which is 180 degree out of phase with the fundamental mode. I can see all those modes. Okay. Now for this fiber I want to check the cutoff wavelength. Means for example the same mode solver method, I'm selecting the finite difference method. Here I'm giving the recalculate, so I'm getting all these modes. For example, as I told you, LP01 is the fundamental mode. For this mode there is no cutoff wavelength. I am calculating the cutoff wavelength for this mode for our understanding. Here I am selecting. Okay, so the theoretical values LP01, it is not available for this fundamental mode. Okay, so I am going to next LP02, that is the higher order mode, LP11 for our. Here I am taking LP11 and here after calculating the cutoff wavelength I am getting the result, that is nothing but LP11, the cutoff wavelength is 3.15. just keep this in your mind, this is normalized cutoff frequency. Okay, similarly for LP02 1.96, for LP21 1.98. Okay, suppose here I want to reduce the number of modes, means here I can change the wavelength. Okay, so as I told you, the number of modes is inversely proportional to the wavelength. So if I reduce the wavelength, then I may get different number of modes. Here I am having 1.2 micrometer. For that 1.2 micrometer, if I calculate the number of modes will be high. Okay, so here I am giving 1.7. For that, the modes LP01, LP02, LP11, LP21. If I increase this to more, then modes will be reduced. Okay, the next one, here I want to show you the birefringence. Okay, so here the lambda value, central wavelength is 1.55. I'm giving okay. For that, the polarization mode dispersion, I'm getting the fiber length PMD data for 1000 meter. Okay, coupling length will be 20 meter. For that, I'm getting the birefringence with respect to wavelength. It is low for 1.35 micrometer, and it is keep on increasing for the increase in the wavelength. Okay, now we have done all these sites, all these calculation. We can see the dispersion graph for this fiber design. This is our profile.